Okay, I think we should start now. It's 10 a.m. So it's my pleasure to have our first speaker, Bertrand Toen, who will talk about the characteristic classes of foliations in positive characteristics. Please.
All right. Thank you very much. Thank you very much to the organizers for inviting me to this conference for this very special occasion. And I'm very sorry not to be able to be presently in Yale now. But from what I can see from the video cameras, the weather in Yale seems fine these days. Is it right?
Yes, and they have commands.
Seems sunny. Ah, okay. Because I think I remember the last time we've met, Sasha,
yes.
I was visiting Yale and it was very, very snowy. And I remember getting stuck at home for 2 weeks and the math department were closed and everything was closed. Yeah, this is quite a memory actually. And yes, of course yeah. Okay, so I mean, when I was visiting, I was giving lectures on shifted symplectic structures, and Sasha was complaining that the shifted symplectic structure on BGLN or BG is always C2, the second Chern class, and he kept asking, but what about higher Chern classes and what they are never used or anything? So in this talk, I will talk about characteristic classes in general, not only C2. So, okay, so it's a joint work with Gabriele Vezzosi. There are a couple of preprints on the archive you can check. And there's also a book in progress. It's very slow progress, but hopefully at some point we will have a book with all of these results written down. And what I want to talk about today is this specific question of what can we say about characteristic classes of foliations in a positive characteristic context. So typically, I'm going to be interested in two kinds of results. There are the vanishing results, like bot vanishing or the existence of residues by bomb bot. And there are also existence results, like the constructions of characteristic classes of foliations, like the Gambillon-Weil invariant is the most famous one, but there is also a whole bunch of characteristic classes based on the Gelfand-Fuchs computations. And so I'll come back to these two results at the end of the talk. But what I want to do is to start with a variety over a perfect field, and I want to try to get these results in crystalline cohomology of the variety. So I'm going to start by reminders about what are these results about, and they are in the complex setting, and then I will explain how it's possible to extend them in a positive characteristic situation. Okay, so let me start with the first one, this vanishing result. So if you start with a holomorphic manifold and you give yourself a holomorphic foliation given by a sum bundle which is stable by the Lie bracket, and if you have a vector bundle which is flat along the foliation, so it comes with a partial connection along the subbundle F, which is given by a map nabla satisfying the usual Leibniz rules and nabla square equals 0. Then there is this famous theorem of Bott stating that if you take any polynomial in Chern classes whose total degree is bigger than the codimension of the foliation, then this polynomial evaluated at the Chern classes of V gives 0 in the Durham cohomology of X. So this is a generalization of the fact that Chern classes of flat bundles are torsion or are 0 in the Durham cohomology. It's a generalization in the sense that you only need if you have a partial connection, then you get 0 after the codimension. And it's often stated for one particular case, which is the normal bundle of the foliation. And this normal bundle comes equipped with a canonical partial connection along the leaf. And that's maybe this corollary is maybe more well known in the literature as a Bott vanishing. And there are also extensions to the case where the foliation has singularities, and this is the existence of residues. And I will come back to this result at the end of the talk. I mean, explain what's the generalization when the foliation has singularities. Okay, that's the first result that I would like to try to extend to varieties over field of characteristic P. And there is another result, which is if I have the same setting, so I have a foliation on X is a holomorphic manifold, then you get this canonical ring map from, so on the left-hand side, little gn is the Lie algebra of formal vector fields on an n-dimensional affine space. N is the codimension of the foliation again. And well, I wrote C, but it's an H. It's a Lie algebra cohomology. There are some issues that this Lie algebra comes with a topology because these are formal vector fields and you have to take only a continuous cohomology. And this X prime is not X, it's the GLN torsor associated to the normal bundle. So it's something that sits over X. And in particular, and maybe this is again, mostly the way it is stated in the literature is when the normal bundle is trivial, you can just pick a trivialization and pull back these classes on X. So you get this way what are called characteristic classes of X in the Ham cohomology of X, just being the image of this map. And so the left-hand side has been computed by Gelf and Fuchs. There are well-known computations of the left-hand side. And so by this map, you get a bunch of characteristic classes. So Godby-Enveille is the very first example of such a class that appears at the image of one of his of a canonical class on the left-hand side. So this is the second statement I would like to generalize to the case of positive characteristic. So to construct such a map of rings from something that is a Lie algebra of something that looks like vector fields on the formal AN to crystalline cohomology of X. Okay, so the first observation is that these results, they don't hold in positive characteristic when you replace the Ham cohomology with crystalline cohomology. And by crystalline cohomology in this talk, I will mean crystalline cohomology with coefficient in the Witt vectors, so integral crystalline cohomology. And so the typical counterexample to the Bott vanishing is the following. Take X to be P1, and as a vector bundle, you take O of P, and O of P is the pullback of O of 1 by the Frobenius. So by this Cartier equivalence, you know that it has a canonical flat connection. But still, C1 of O of P is not zero in crystalline cohomology. So you cannot get vanishing in crystalline cohomology just knowing that you have a flat connection. You need more than this. So you cannot expect Bott vanishing results to be true without extra conditions. That's the first statement. And it's a little bit the same thing for the second statement. If you want a map like this, you will have to modify a little bit the left-hand side to have something compatible with the crystalline cohomology. So we will see at the end where we have only partial results there. So, but ultimately what you would like to have is some vector fields on maybe not a formal AN, but formal AN with divided powers and this kind of thing. So there are some divided powers involved in this story, and to be able to get this map. Okay, I'll be back to this at the end. So this tells you that the extension is not automatic. I mean, the results fails, and you have to restrict the class of foliations for which you can expect this to be true. And so this is what I'm going to do now. I'm going to spell out some extra conditions on F. These are not exactly extra conditions. They are extra structures. And the map involves, for instance, this characteristic classes map will depend on the extra structure we pick. So it's not only a condition. And that ensures that these theorems and these results, these constructions make sense in positive characteristic. Okay, well, so what's the basic idea is always the same thing in crystalline cohomology. You have your smooth variety over spec K. K is a perfect field. you introduce the Witt vectors over K, and you look at X as a scheme over the formal spectrum of WK that I will call S. So now it's a very degenerate situation because you have X sits vertically on some kind of p-adic disk, right? And what you want is that the foliation should extend over S, so it should like behave like a crystal, so it should extend in the zero characteristic somehow. So that this extends over S is what I'm going to make precise. Now, the problem with this thing is that X is definitely not smooth over S. It's even not flat. It's a very degenerate situation. And if you want to talk about foliations on X relative to S, this is a very bad situation because you have to talk about foliations on non-smooth schemes, even non-flat schemes over the base. So you're in a situation which is very singular. And this is why tools from Dirac geometry are useful in this context. Okay. And maybe I should say here, I will never assume that X lifts in characteristic 0. So X might not lift as a variety to a smooth schemes over S. Still, it's possible that the foliation extends in some sense without the scheme extending. This is what I'm going to explain. Okay, so if you in such a situation, if you want to talk about foliations on non-smooth schemes, the first thing to do is to replace one forms or the vector bundle of one forms or the vector bundle of vector fields by the derived analogs. So you have to replace one forms with the cotangent complex. And this is what we're going to do. And then you have to define what are foliations using cotangent complexes instead of one forms. Okay, and this will lead us to a notion of derived foliation that I'm going to explain now. Okay, so what's the vague ID? The vague ID is pretty simple. Suppose you have a morphism of schemes over any characteristic. It could be worse than schemes. You can have derived schemes or derived stacks if you want. And you want to say that a derived foliation on X over S will consist of two pieces of data. The first piece of data will be a cotangent complex. So it will be a perfect complex of OX module L. And you want to think of L as the complex of one forms along the leaves of your foliations. So you think of L, that's what is going to replace omega 1 of the foliation. Okay, so forms along the leaves. So this is going to be the dual of the tangent complex. And then the second piece of data is a de Rham differential on this L. So you want a differential on the symmetric algebra over L with a shift. And it has to be compatible with the grading, of course, and it has to be compatible with the algebra structure. And this differential will induce a derivation from OX to L, and it has to be compatible with the already existing differential on the cotangent complex of X. So there is a compatibility between D and the usual de Rham differential on the cotangent complex of X. So that's a pretty simple idea. It's if you unfold these definitions, it's just a point of view where you define foliations by being differential ideals in the de Rham complex. Right? You can define a foliation not by being a subbundle of the tangent bundle, but a subbundle of the one forms which generates a differential ideal, which is stable by the de Rham differential. So that's the idea which is behind this definition. So there is a major issue here. So if you want to make this precise, the problem you face, and this is typically related to a non-zero characteristic, is that this symmetric algebra must be understood in the sense of simplicial rings. Because if you do the symmetric algebra in the sense of commutative DG algebra, this is badly behaved in non-zero characteristic. And so on one side, you have this simplicial object, and D is a differential, so it lives more in the world of complexes. So when you try to say what is the condition what's the compatibility between D and the algebra structure, it gets quite complicated. And in characteristic 0, you can resolve all of this just by using a commutative DG algebras. And then D is just a multiplicative differential. But in the simple setting, it's a complicated story. So that's what I'm going to explain now. And I must say that it sounds overcomplicated in some sense, but at the moment we don't have any simplifications of the definition we have. So it seems inherent to the subject that this compatibility between D and the simple algebra structure is a complicated thing. And the way we will talk about it is oh, sorry, maybe there's a, yeah, so the fact that the interaction is complicated, it's always the same thing, is that you want to normalize your simple algebra to get a complex, but then you have a failure of symmetry of the Alexander-Whitney maps. And so the normalization is, there is a complication. I mean, you don't have an equivalence between commutative simple algebras and commutative DG algebras, such things. So that's why it's a complicated story. So the idea here is to represent this D as a group action. So we're not going to talk about differential anymore, but we're going to take this symmetric algebra as a simple algebra, take its spectrum as a derived scheme, and say that on this derived scheme, we have a group action on a certain very explicit group, and that this group action represents the Durham differential, this differential D. Okay, so let's now, if there are no questions up to here, I will start getting more precise definitions about what is this group. So I will have to describe this group. So this group is called the graded circle. It's called the graded circle because we realized that it's the associated graded of a filtration on the usual circle, but it's not the topological circle. There is a big difference between this graded circle and the topological circle. So it can be defined purely algebraically in the following way. You take the ring of divided powers with one generators, Z of X, which by definition is the subring of Q of X generated by divided powers. And you look at it as a Hopf algebra, because the Hopf algebra structure on QX, the additive Hopf algebra structure, restricts to a Hopf algebra structure on divided powers. It's a commutative and co-commutative Hopf algebra, so it defines an abelian group scheme. And this group scheme is called KER. I will explain why it's called KER in a minute, which is the spectrum of this D, so D is Z of X here. And by definition, the graded circle is the classifying stack of this KER. So it's B KER. So it's a group stack. It's a stack with a group structure. The group structure comes from the fact that KER is abelian. So its classifying space is a group. And it's, if you want this group scheme KER here, replace what Z is when you write the topological circle as BZ, but it's not a discrete group anymore. It's one of these group scheme, which is it's actually a group scheme which is pretty complicated because it's not even of finite type. Okay, so this is a group stack over spec Z. This lives over spec Z. And we can compute its fiber over fields to have an idea of what it means. And in characteristic 0, this graded circle is just the classifying space of the additive group, just BQ if you want. So it's just a rational circle. And in positive characteristic, it's the classifying space of a non-reduced group scheme, which is KER-P. And KER-P is the kernel of the Frobenius on Witt vectors. So you have this group scheme of Witt vectors. You have the Frobenius endomorphism, and you take the kernel of the Frobenius. So because this W is a successive extension of additive groups, this kernel is a successive extension of the kernel of the Frobenius on the additive group, which is this group alpha P I'm talking about. So it's a KER-P is like it's a pro-algebraic group, which is a successive extension of finite flat group scheme, which are kernel of Frobenius on GA. So it's very non-reduced. It has actually a unique point. It looks like a formal group, and one way to understand it is you want to think as a degenerate version of Z, in the sense that if you look at Z as a discrete group scheme over spec Z, it's just an infinite number of points. You can think that these points collapse together in a very big fat point, a very big scheme point, and the group structure is preserved. And this is what you get when you do this. You get this CAGP. So it's really a degeneration of Z in some sense. Okay. So this graded circle is not, it has some relation with the circle, of course. Its cohomology groups are the same as the circle. So the cohomology algebra even is the same as the circle. So if I compute cohomology of the graded circle with coefficient in functions, I get the cohomology of the topological circle, Z in degree 0 and Z in degree 1, and the multiplicative structure is just the obvious one. But at the level of chain complexes, this is not true. So if I look at the chain complexes endowed with their E infinity algebra structure, these two things are not quasi-isomorphic. So the cohomology of the usual circle and the cohomology of this graded circle are not the same. And the difference is that by construction, almost the cohomology of the graded circle is formal. So it's equivalent to its cohomology, but the cohomology of the topological circle is not. So this is something we've learned, and it's very well known from topologists, is that spaces are almost never formal over Z. Formal in the sense of rational homotopy theory. So for instance, there is a very nice talk by Mike Mendel, and I think he has notes on his webpage, where he explains why spheres are not formal over Z. So this is just the case of a circle. So this cohomology algebra of the circle over Z is formal as an E1 algebra, but it's not formal as an E2 algebra. So it cannot be formal as an E infinity algebra. And the difference between, so this graded circle is exactly, if you want, the formalized version or the formal version of the topological circle. Okay, so that's, so one has to be careful that this is not the usual circle. And because these spaces are never formal over Z, this graded circle is not it cannot be associated to any topological spaces. So its cohomology is not the cohomology of space, something else. So it's not something you can get out of topology. Okay, and that's the group that we're going to use to define the Ham differential. This is where it comes from. So if I have this group stack, I can look at its representations. So representations are going to be complexes with actions of this group stack. And you can prove that they are exactly mixed complexes. So maybe I can state this as a proposition. You have an equivalence, and this equivalence preserves the symmetric monoidal structure on both sides between the representations of S1 Greux, which are defined as quasi-coherent complexes on the classifying stack of S1 Greux. So, a quasi-coherent complex of BS1 Greux is a quasi-coherent complex with an action of S1 Greux. And on the other side, you have mixed complexes, and with the usual tensor product of mixed complexes. So mixed complexes are by definition DG modules over this DG algebra, Z of epsilon, where epsilon is of degree -1. So this explains why action of the graded circle are differentials. And the fact that this equivalence is symmetric monoidal is important. So because it's going to be very important to, if we want to say that the differential is compatible with some algebra structure, we need a symmetric monoidal equivalence. And I should say here another consequence of the difference with the topological circle is that this proposition is wrong for the usual circle. There is an equivalence, but it's not symmetric monoidal. So it's hard to believe, but that's life. There is an equivalence of categories, but the tensor product on representation of the circle and the tensor product of mixed complexes are not the same. And yeah, so to put this in differently, the circle and the graded circle, they share the same category of representations, but the tensor products are different. So they are the same categories, but different as symmetric monoidal categories. Okay. Yeah, and that's not just a comment that you can actually say that S1 GRE is the associated graded of a filtration on S1 in some sense. So we have this paper with Tazos Molinos and Marco Roballo explaining this HKR filtration, that there is a way to say that it's the associated graded of something. I'm not going to get into that now. But... Okay. So now this graded circle, it's graded, so it has an action of GM because it has a natural graduation, and I can look at the semi-direct product. And this group H is really the group I'm interested in because representation of H will be graded complexes together with a mixed structure that is compatible. So a representation of H is a graded mixed complex. And I want to keep this graduation in the picture. That's important. So now for scheme X, now that I have this graded circle, I define the graded loop space to be maps from the graded circle to X. And X is a scheme here. S1 GRE is a group stack, and this map is a Dirac scheme. So this is an internal home inside Dirac schemes. So it's the scheme of maps between S1 GRE and X. And it comes equipped with a natural H action by this semi-direct product. So it means it has a grading, it has a GM action, but it has also a S1 GRE action. So the S1 GRE action is by rotation. So it's just the usual action of the circle on the loop space by rotations. And the GM action is just the induced grading. And as such, this H action will be important in a moment. So now if I do this, what you can prove is that this, if you look at you forget the H action, you just look at the Dirac scheme of L GRE X, what you can prove is that it is exactly the spectrum of the seam of Lx shifted by 1. So that's, it's a version of the HKR, I mean, I don't know how to say that. It's some kind of HKR theorem, if you want. And I will also denote this by the odd tangent space Tx shifted by -1. And now I have this action H on this odd tangent space. And by definition, this action encodes the Durham differential. And as it is an action on the Dirac scheme, it's compatible with, it's an action on the affine Dirac scheme. So it's an action on the simple algebra. So it is compatible with the multiplicative structure and the grading. And you can prove that when you normalize and you just look at it as a complex with a differential, this is the Durham complex. This is the Durham differential in the usual sense. If you do all of this with the circle, the non-graded circle, what you would find instead is Hochschild homology with the Kohn operator instead of forms with the Durham differential. Now, this action here, it's so by construction, it's an action of a group stack on the Dirac scheme. If you want to describe this purely algebraically, it's a bit complicated. There is a work by Harpon-Raksit, which is purely algebraic. There is no mention of stacks or derived stacks or anything. It's purely, but it uses infinity monads, and it's not really simple in a way, but it's purely categorical, I would say. It's a purely categorical approach. There is an infinity monad on complexes for which you can, and there are infinity Hopf algebras, and you can look at comodules over these infinity Hopf algebras and so on. So there is a way to construct these things without using stacks and schemes and things like this. But it uses a very heavy machinery. And infinity operads are not enough here. These infinity monads are not operads. So there is really some technical complications. Okay, so this was the absolute situation. Now you have a relative situation. If you have a map of schemes, there is a relative graded loop space where you want to think of map from the circle in the fibers of X over S. So you can construct it as this fiber product, and it gives you the odd relative tangent space. And it comes equipped with an action of H, and this gives you relative, the relative Durham cohomology. And that's a consequence of what I've just said. If you take the cohomology of the graded loop space with coefficient in the structure sheaf, and you take invariance by H. So invariance means cohomology here, means homotopy invariance by H. You get a complex which is naturally quasi-isomorphic to the derived Durham cohomology. And there is a little hat in the sense that there is some completion with respect to the Hodge filtration. When X over S is smooth, this completion is not there. It's already complete because the Hodge filtration is finite. But when X over S is not smooth, this completion thing is very important. And this is what you get by this construction. So the derived Durham cohomology is obtained by H equivariant functions on the graded loop space. Okay. So in particular, if you're over a spec C, this computes algebraic Durham cohomology even when X is singular set. So if X is a scheme of finite type over spec C, this computes algebraic Durham cohomology. So there is a well-known isomorphism between completed derived Durham cohomology and algebraic Durham cohomology. Okay. Now let me go to foliations. So I have X over S. I want to define foliations on X relative to S. So foliations in the fibers, if you want. So it's a family of foliations on the fibers of X over S. And I do it like this: a derived foliation on X relative to S. It's going to be a derived scheme F with an action of H. So remember, this action of H encodes a grading and a differential. I want a map from F to the graded loop space. That's going to be my anchor map. If you think in terms of, if you keep in mind foliations being Lie algebroids, for instance, you have the map to the tangent vector bundle. The anchor map is this map from F to the graded loop space. And then you need a condition, is that if you forget the action of the circle, and you just look at it as a graded scheme, it's just a seam of some complex. So, so it's a little bit complicated as it seems, but naively, it does exactly what I was talking about at the beginning, in the sense that you really want to say that F is determined by the complex LF, because it's the spec. It's, if you want, F is the total space of LF. It's the spec of its symmetric algebra, and then. So you give LF, and then you give an action of H on the symmetric algebra of LF shifted by 1. And the map from F to the graded loop space over X is the compatibility with the already existing Durham differential on X yeah. So this is what it is. It's a definition, and it works in the sense that I mean, if you are in characteristic 0 and in a smooth case, this definition of a derived foliation recovers smooth foliations as a particular case. It also recovers some Lie algebroids, you know, like groupoids actions, some infinitesimal groupoid actions, these kind of things. And it also recovers DG Lie algebras if you work over a point and this kind of thing. So it's a definition that works very well in characteristic 0. And we were not sure that it was very interesting in non-zero characteristic, but it turns out that you can use these to prove both vanishing results as well as the existence of characteristic classes in positive characteristics. So it's a kind of useful definition. I'm not claiming it's the right definition of a foliation outside of characteristic 0, but at least it's a useful definition. Okay, I don't know, are there questions about this? Seems no. Okay. Okay.
I have two questions. So,
Sure.
let's say so in the as in the beginning of your positive characteristic case, right? So, but you now if you choose your x over spec k and s to be the expression of the real weighted vectors, but you can also take like a truncated weighted vectors, right? I mean, you can like shrink it. It's like a
You
shrinking.
can also take what? Sorry, I didn't get it. You can also take.
So your S can change, right? You can enlarge your S or like
Sure.
shrink your S if your X is supported on some closer points of S, right?
Yes.
And so how does this how does the foliation change? Like if you change your S?
Yeah.
I mean,
So you see this graded loop space relative to S depends on the base. So
yeah, depending on basis, how does it change?
It depends on the base. So the notion of a foliation relative to S depends on the base. So foliations of X over K are not going to be the same thing as foliations of X over S. It's even worse, I think. There is a map from foliations of X over S to foliations of X over K, which is like pullback. I will talk about it in a minute. And this is not, it's not essentially surjective. It's not fully faithful, or so the fact that spec K is a closed subscheme in S is not useful here, because in Dirac geometry, a closed immersion is not a subobject. It's not a monomorphism. So in Dirac geometry, a closed immersion can have a lot of automorphisms. The automorphism derived group of a closed immersion is not trivial. So that's why, yeah.
So
you can think in terms of Dirac categories. So the Dirac category of a closed subscheme is not a subcategory of the Dirac category. Yeah.
Okay. Yeah. Thank you. Yeah. So like, let's say, if your X can be lifted to a smooth family over the whole S, and does this give you something?
Yeah. I will say it in a minute. So this, if everything is liftable to S, then there is an obvious lift for. I mean, let me continue, and I will come to this. Yeah.
Sure. Thank you.
Okay, so let me give some very, very basic examples. First, they form an infinity category. So you can have map from F to F prime that is equivalent with respect to H, and that commutes with this map to the graded group space. So they form an infinity category that's going to be denoted full of X over S. It has an initial and a final object. And these initial and final objects are very easy to identify, and it has also finite limits. So finite limits is not completely obvious. I mean, if you think you have two smooth foliation on a smooth variety, you want to intersect them, and the leaves are going to have singularities, for instance, if you don't have transversality results. So that's a way to form interesting derived foliation out of smooth foliations. Suppose you have two foliations which are not transversal, you can intersect them and get a Dirac foliation that way. So the initial object is the zero foliation, is when the cotangent complex is zero. This is where the leaves are just the points, just the stupid foliation. And there is another stupid foliation where there is only one leaf, which is where LF is the whole cotangent complex. So F is already the graded loop space of X. So that's are denoted by 0 and star. That's the initial and final object. And and in the second case, the leaves are just the fibers of X over S. And one very important construction is that you have pullbacks. So if I have a foliations on X over S, if I have any map, so it's a pullback that acts on X, but also on the base. So if you have a commutative square like this, you get a pullback. This is also interesting because suppose that X prime and X are smooth schemes, and you have a smooth foliation on X, but the map F is not transversal with respect to the foliation. You can still pull back as a derived foliation. So again, it's a context where if you pull back a foliation by any map, usually the thing you get is a singular foliation because the leaves will have singularities. So that's a very easy way to construct derived foliation out of standard smooth foliation just by pullbacks. And then if you have pullbacks, you can define what are the globally integrable foliations. So they are the ones that are pullbacks of zeros. That's by definition. So that's one way to define what is globally integrable for a foliation, just pullback of zero for some map. Okay, and then when X is, then there is this comparison with the world, the standard notion of a foliation on a smooth scheme. If X over S is smooth, and if you look at some bundles which are differential ideals in omega-1, you can see these as derived foliation in the sense of the definition I just gave. And it's not an easy statement. So I mean, everything is complicated in these definitions, and in particular, something very simple that you just have a sub-bundle, and you know that it is stable by the Durham differential. So what you know is that on the quotient bundle, omega-1 divided by the ideal, you know that there is an induced Durham differential, and you want to say that this induced Durham differential is an action of H. I just defined. You have to work quite a bit to prove that, actually, but it's a theorem. So that you can see these differential ideals as derived foliations in the sense I just gave. Okay, I'm not going to insist on this, but maybe there is a simple proof, but I couldn't find any simple proof. So. Okay, now I'm going to talk about cohomology of foliations. So suppose you have a derived foliation, you can define its derived Durham cohomology. So by Durham cohomology of a foliation, you should think of Durham cohomology along the leaves, so longitudinal cohomology. So classically, you mod out the Durham complex of X by the differential ideal, and you take the cohomology of the result. And this can be defined simply in terms of, again, you take cohomology of F. F is my derived scheme, which is the foliation with coefficient in O, and I take invariance or homotopy invariance by H. That's the standard definition. And there is a little hat in the sense that it's always completed along it's a completed version of the Durham cohomology along the Hodge filtration. And you can define, can name this derived longitudinal cohomology. And the explicit form is the following. It's an infinite product of wedge powers of the cotangent complex of the foliation. And the differential is a total differential. There is a little d which is internal to L because L is a complex itself. And there is an external differential which is the Durham is this action of the mixed structure given by the action of H. And you take the total complex of that. So the underlying complex is pretty simple. It's just this guy. So it's something very close to I mean, it's the cyclic cohomology complex associated to a natural mixed complex. Okay, and we have to be careful that it's an infinite product and not a sum. So of course, when LF is a vector bundle, this infinite product is finite, but in general, you have this completion appearing, and so the completion is related to the fact that it's an infinite product and not an infinite sum. Okay, here is another statement, which is also, that's a generalization of something very well known for smooth foliations, is that if you give a derived foliation on X, it defines a canonical descending filtration on the Durham complex of X. So that's the Durham complex of X over S. And the first graded piece is this longitudinal cohomology. And the filtration is compatible, it's functorial, and it's also multiplicative. So that's a generalization of the fact that for foliation, it gives a filtration on the Durham complex of the ambient manifold. And so the first piece is just the Durham complex where you mod out by the differential ideal. And then the next pieces are actually Durham complex, longitudinal Durham cohomology, but with coefficients in the conormal sheaf or wedge powers of the conormal sheaves. So N here is the conormal complex, or conormal bundle in the smooth case. So that's something very important for this bot vanishing, because bot vanishing arises by saying that something in zero on the grow, something is zero on the grow zero. And then as it is multiplicative, it lives in this F1. And if you multiply enough, you get in FD. And if FD is zero, you get the vanishing. So that this multiplicative property of the filtration is very important here. Okay. So you can define what does it mean for a vector bundle or a perfect complex to be flat along F. One way to define this is the following. Your perfect complex is a map from X to the stack of perfect complexes, or if it is a vector bundle, it's a map from X to BGLN. And you want to say that if you precompose with the map from F to X, so F sits over the grid loop space. The grid loop space goes to X by evaluating at the base point. So you have a map from F to X. So it gives you a map from F to parf, and you want this map to be promoted to an H equivariant map. So it's an extra structure. It's not really a property. So it's like the data of a connection. So you say that a connection on E along F is by construction an H equivariant structure on this map F to parf. And H acts trivially on parf, and it acts trivially on X. So that's the definition. And if you unfold the definition, you can describe this. I mean, get convinced that this is just a map from E to E tensor LF, and but you have to say that its square equals 0, and to say that the square equals 0 needs a lot of homotopies and so on, and they are all encoded in this this definition here. Okay, so that's just a way to say that it's infinitesimally constant along the leaves. Okay, now you have this this proposition says that if I have a perfect complex on X, which is flat along a derived foliation, if I look at it, so it has Chan classes in the Ram cohomology, in the Ram cohomology of X over S. If I project from the Ram cohomology to longitudinal the Ram cohomology, then I get 0. The statement is a little bit more than this. It tells you that on the level of chain complexes, these images have, there is a canonical homotopy to 0. It's stronger than just being 0 in cohomology. The choice of a connection on E along F gives you a choice of homotopies from the Chan classes to 0. So that's again a generalization of something very well known, that if you have a partial connection, the Chan classes in a longitudinal Ram cohomology are zeros, which you can, for instance, check by Chan veil theory, something like this. Okay, so now I think I have everything I need to talk about these two applications. So let me talk about residues, which is this generalized version of bot vanishing to the case where you have singularities. So I have a base perfect field, it's ring of Witt vectors, and S is the formal spectrum of Witt vectors. And I have a smooth algebraic variety X over little k. And now I give a coherent subsheaf, which is a differential ideal. So singularities appears precisely when this coherent subsheaf is not a subbundle. So there is a locus, say there is an open in, or U is not an element in X, it's a subset in X. So there is an open U in X, and on which this D is a subbundle, and that's the open where the foliation is, I mean, where the differential ideal defines the smooth foliations. But on Z, you have singularities. And I let by Q the rank of D on this open subscheme. Okay. And now, under these conditions, assume that I have a so this D restricted to U gives me a foliations on U in the most standard way. But now assume that it extends to a foliation of U over S. So extends means there is a derived foliation F prime. If I pull it back to, so spec K maps to U, so I have this pullback from foliations U over S to foliations U over K. I just pull it back to the close point. And so extends means I have this f prime so that the pullback recovers f. Then I have this existence of residues. Then for any homogeneous polynomial in the Chan classes, which is of degree bigger than the codimension, I don't get vanishing because of singularities, but I get that the phi evaluated at the Chan classes localized along Z. Z is the singular locus. So there is a canonical well-defined class, which is a cohomology class with supports in Z. It lives in crystalline cohomology with coefficient in WK. And if I send it to the cohomology of X, I find this, this polynomial. So if Z is empty, so it means there is no singularities, I do get the vanishing results. If Z is not empty, it's this generalization by Bohm and Bott, which is this existence of residues. This class is called the residue of the foliation. Yeah. And see, okay. So that's the first statement. And the statement is wrong if I don't assume that f extends to an f prime. So I do need these extensions. It's even more than this. I think if this residue class depends on the choice of f prime. So a priori, there is no reason why this residue should be independent of f prime. So if I pick an f prime and pick an equivalence between its pullback to u over k and f, this defines this residue, but if I change f prime by something else, then maybe I do get a different class. And then about these characteristic classes, let's suppose that we have in the same situation than before. So X is a smooth variety over K. K is perfect of characteristic P. I have now this statement is only rational. So we think there is an integral version, but we don't know how to do it now. So I have the fraction field of the Wick vectors now. And suppose that I have a differential ideal, and which is a subbundle now. And again, assume it has a lift, or f prime over S. Then you do get this map. So if I look at X prime, which is the total space of the normal bundle over X, you have this canonical map. And now this is crystalline cohomology with coefficient in K. So it's rational crystalline cohomology. It's not, it would be nice to have integral results, but the left-hand side is unclear. And the left-hand side here is the usual thing, but over BK. So it's the Lie algebra of formal vector fields over K, over BK. And it just, I don't know whether there is a hat on G. It's just a continuous Lie algebra cohomology. Okay. So I'm not sure if I, yeah, this is what I'm convinced that there is a way to get an integral statement, but what should be the left-hand side is a bit mysterious. There is something we can write down, but it's very complicated. So I don't know. I don't know if there is. It would be nice to have something better than rational crystalline cohomology, but at the moment we don't know. Yeah, maybe I will finish by explaining what are the three main ingredients to prove these two statements. So I have this existence of residues and these characteristic classes, existence of this characteristic homomorphism. And so the main ingredients are the following one. The first thing is that the conormal bundle of a foliation always have a partial connection along the foliation. And if your foliation lifts over S, then this conormal bundle also lifts over S. So this bundle is not only a bundle, it's like a crystal in some sense along the leaves of the connection. So that's the first observation, that this conormal bundle is always flat along the leaves. Then there is this vanishing theorem for Chen classes, which is kind of formal actually. This is just a formal diagram chase. I mean, you just have to, that the Chan classes in longitudinal Doham cohomology of a flat perfect complexes along a foliation are zero. I mean, they are not more than zero. They are canonically homotopic to zero. And then the key point is that there is a very close relation between these derived de Rham cohomology. So I mentioned several times this Hodge completed derived cohomology, de Rham cohomology, to the crystalline cohomology. They are not exactly the same, but you can actually prove that there is a canonical isomorphism. I think this version is due to Bargath-Batt, but there are partial results by Ilusi in his thesis, where you compare the derived de Rham cohomology of X over S. So X is over spec A. I look at it as a scheme over S. So it has this derived de Rham cohomology of X over S. It's not crystalline cohomology, but I can make this base change. So I can tensor over the de Rham cohomology of little s over S. Little s is spec K by the Witt vectors. And then I find back the crystalline cohomology of X over WK. This is only true for X being smooth over spec K. But there is a way to essentially crystalline cohomology and derived de Rham cohomology are you can write that you can exchange from one to the other by just some simple formulas. So this vanishing theorem, the second statement, which is this vanishing theorem for Chan classes, happens in derived de Rham cohomology, but using this result, you can get the vanishing in crystalline cohomology. So that's the same. In the same way, you can these characteristic maps from the Lie algebra cohomology to the crystalline cohomology. A priori, it goes to the derived de Rham cohomology, but you can project down to crystalline cohomology by this canonical isomorphism. So this is how you construct things. And this, maybe as a final comment, I should say that the fact that this derived de Rham cohomology is not exactly crystalline cohomology make me think that these derived foliations are not the best thing possible. There should be a way to define crystalline foliations in some sense. I mean, I don't know how to do this really, but to define a notion of foliations for which the cohomology gives automatically crystalline cohomology without this weird formula. So this is what I was saying at the beginning, that it's not completely clear that this is the best possible definition of derived foliation outside of characteristic zero. And they could be something more with more crystalline features, say, but at least it's useful to prove these results. Okay, and I think I've finished now.
Thank you very much. Are there any questions?
Actually, I have a question, if possible.
Please.
Oh.
Bertrand, hello?
Yes, I'm here.
I have a question or suggestion. In usual situation, if you have a complex manifold and have a complex flat bundle over manifold, of course, the Rham cohomology vanished by the Bot-Chern value by using connections, but there is a much stronger theorem due to Reznikov that actually characteristic classes with values in the link cohomology torsion or in rational link cohomology are equal to zero. You know that?
Yeah, I've heard about this result, yeah.
And so listening to you, I would suspect that something like this happens in positive characteristic. And here's a guess how it might go. First of all, so what you did, you said, we are talking about extension of Bort's vanishing theorem. So you need to have a foliation, and you explained that characteristic classes for degree bigger than twice codimension of a flat bundle in this foliation are zero in the Rham cohomology. Now, in finite characteristic, first of all, let's consider the analog of the link cohomology, which is symptomic cohomology. So I would think that you can define characteristic classes of appropriately defined foliations with values in symptomic cohomology. And actually, if you do this for characteristic classes of flat bundles on foliations, they will be analog of Bot theorem that in degree bigger than twice codimensions, they also will be zero. And unlike the result about the Rham cohomology, which is obvious just because the curvature is given, the Chern class is given by the curvature, this theorem is highly non-obvious in any.
Yeah, I understand this. Yeah.
So maybe that's maybe
that's a very nice observation. Yeah.
So maybe
Bot. Yeah. Because Reznikov's proofs uses non-abelian Hodge theory, right? It uses the fact that any local systems can be deformed to a variation of Hodge structure, right?
He used lots of things, yeah. but the
But,
statement,
are there already results in that direction for the tautological foliation, just for just flat bundles?
I'm not sure. I'm not sure.
Or some kind of crystals or F crystals? I don't know.
No, I don't know any extension of Reznikov's theorem.
Oh, that's a very nice observation. I will have a look. So my guess is that you cannot avoid this kind of existence of lifts, this F prime, in the sense that I mean, again, you have this example of O of P being a flat line bundle on P1, and its C1 is not zero. So even in crystalline cohomology. So I guess. So the centromic cohomology has a map to crystalline cohomology, right?
Yeah, I mean, centromic cohomology is P analog, I would say, of the Hodge cohomology. They are all kind of shadows of Mathieu cohomology.
So my guess is that you wouldn't escape the existence of this F prime, and so I didn't comment about this at the end. But so. It's a very complicated thing to check that when is a foliation admitting when does F admits an extension to S is a complicated thing. So of course the tautological foliation, so the finite foliation has an extension to S, even if X doesn't extend to S. That's just because saying that F extends to S in a way means that the leaf space doesn't exist, but suppose that there is a leaf space, which is a quotient of X by the leaf space, by the foliation. Then you want the leaf space to extend as a smooth thing over S. So the leaf space of the total foliation is a point. So a point extends, it just extends to a point. So this is why for the tautological foliation, this extension, there is a canonical one. But then for a general foliation, this F prime will exist when the quotient in some sense is a liftable object over S, and that's a very complicated thing to check, I think. So it's a non and maybe to answer the question 10 minutes ago, if you know that the scheme X lifts to a scheme over S and the foliation F lifts to a smooth foliation on X over S, then this F prime exists tautologically. So of course, if the foliation extends, if the scheme and the foliation extends, everything extends. But there is this funny situation where you can have a scheme over K that doesn't extend over S, but still the foliation does extend over S, because extending the foliation means extending the leaf space. So in a way, the leaves themselves, they don't extend, but the leaf space extends. It's a bizarre thing. And my impression is that you cannot avoid this. So in the sense that, all results fail without this condition, I think.
Yeah, I was trying to say that for appropriately defined notion of foliation.
No, I understand. The thing would be to, what's a centromic cohomology with coefficient in a foliation or something like this. No, I perfectly understand.
And also,
thank you for the comment. Yeah.
Sure. And also I wanted to make a historical comment. The story about characteristic class of foliations, there was two people somehow related to, there was one idea suggested by two people. First was Gelfand's idea of formal geometry, and this was its ICM 1970 talk at Nice, and then developed with Fuchs and Kazhdan. And this led to characteristic classes, Bernstein, Rutherford, and so on. On the other hand, the idea of formal geometry was that you can do topology in a point, but you need formal vector fields. But then the same idea was suggested by Grothendieck, and you can find it in this expose. And Grothendieck was concerned by crystalline cohomology. So it is interesting that you combining now two things.
I see.
I was just wondering whether if you can trace back the origins of this, the same idea in minds of these two people.
Actually, I don't know. I mean, no. I mean I didn't make any connections between Grothendieck crystalline cohomology and formal geometry of. I mean, the only. I mean, at the beginning, we were doing everything in characteristic 0, and we were playing with results in characteristic 0 and having this we were trying to prove some results in characteristic 0 for foliations with singularities. But then this group stack, the graded circle, came up. I mean, with this HKR filtration. So we just discussed this with Tazos and Marco, and I just realized that this was the missing piece to define foliations in non-zero characteristic, or at least to give a definition of foliations. And I don't know. I just test. It was just by pure curiosity that we say, okay, can we prove some standard results on foliations in characteristic P using this definition as a test? And we discovered this notion of lifts that way. So just I didn't make the connection you mentioned. Maybe it was unconscious. I don't know. Yeah.
But just to finish with this, the first comment. So the idea of this behind Reznikov's theorem is a claim that you can define cohomology as well as Chern class with values in the-link cohomology. And if you think about this one way, it's a kind of the loop, I don't know, the usual Chern-Vane construction. That's what the-link cohomology that's what Chern class and the-link cohomology in a sense are. Something like that should be true in your system with symptomic cohomology. Okay, that's all I want to say.
Yeah, thank you.
And thank you for the great lecture. You always think about fundamental things.
You're welcome. Thank you.
Are there any other questions?
Yeah, maybe a quick question. So the classical theory of characteristic classes of foliations has some applications in distinguishing foliations or showing that deformations of foliations are non-trivial and so on. Can we have such applications here?
I don't know. It's a great question. I don't know. The thing is that I'm completely new to the notion to foliation, so I don't know anything. So I'm sure that there are plenty of results I should. So I will have a look. I don't know. Yeah. I have no idea really. There is one thing we want to investigate. I'm sorry, I'm going to answer another question maybe, but there is one thing we want to investigate which seems also classical. So usually in characteristic P, so I think Toen Ekedal did study foliations in characteristic P and explained that the correct notion of a foliation is not a sub-Lie algebra in the tangent bundle, but it's a restricted sub-Lie algebra in the tangent bundle. So there is also always that this subsheaf in the tangent bundle should be stable by the pth power. Should be a restricted Lie algebra. And this is something that never appears in our work at the moment. So there is no Frobenius acting anywhere. So I suspect that this lifting F prime has something to do with Frobenius type of thing. So like has something to do with the foliation being compatible with the Frobenius on X in some sense, but this I don't know. So yeah, I'm sorry. There are many things in foliation I don't know. So I don't know what to answer to your question. So, but I will have a look.
So this condition of having divided powers that you mentioned from Ekedal, it seems that this should be related to local formal integrability of the reaction.
Exactly.
But you said, but on the other hand, you said that is not enough for your theory to work. Not it should be what you have is liftability to characteristic 0 rather than integrability.
Yeah, exactly. Yeah, this is stronger. Yeah.
But does it imply does your condition imply local formal integrability? Probably. Like on the formal neighborhood.
It depends what you mean by formal integrability, because.
So I mean, suppose you have a smooth foliation on a smooth variety, and take a point. Is it true that on the formal neighborhood of this point, this foliation is trivial? Like
on the formal neighborhood, I don't think it's true, but with our definition, I think it's true on the divided power formal neighborhood. So there is like a PD formal local integrability, something like this. In characteristic 0, it's true. So the derived foliations are always formally locally integrable. even if you have singularities and all these things, the fact that you have this derived foliation structure gives you formal integrability. And in characteristic P, my feeling is that you do get a divided power version of that. So on the divided power envelope of the point in the formal completion, you do get integrability, but not on the formal completion.
Yeah, so this is has to do probably exactly with the Seckerdal condition. If you add that condition, then it will imply ordinary formal integrability.
Ah, I see.
Maybe.
I see. Yeah.
Okay, thank you.
Thank you.
Okay, let's thank the speaker again for a beautiful talk. So our next talk will resume at 11:30. So
okay, thank you.
Thank you very much.
Thank you, Bertrand.
Thank you. I'm sorry, I will have to leave, so I cannot attend the next talk because because of kids at school. So
Different time zone, yeah.
Yeah, I'm very sorry about that. But thank you again. Yeah. Bye-bye.